let's talk about another really useful modeling tool, and that is the idea of boiling a set of numbers down to one number so we can say if it's better or worse than some other set of numbers. Here I've got a set of points on a scatter plot, and I might want to come up with a function that describes that set of points, and not just those points exactly, but that general trend, so a trend line maybe. I have no strong evidence of nonlinearity here. If there's some kind of statistical error, I wouldn't expect them to fall exactly on a line. So I've got a trend line function programmed in here, and I've got some sliders, and I can play with the slope, and I can play with the intercept. And so I could, by eye, adjust the slope and the intercept until they look like they're doing a pretty good job coming near the line. What do you think? Coming near the data points? Does that look pretty good? And I've got my x and y here, and I can show that these are the values of the trend line, or so at each particular x value, these purple points are what the trend line is predicting at that x value. So I came up with like b equals 10 and m equals 4.4. Maybe someone else came up with some other values that they think are pretty good. Or even if I just did this tomorrow, maybe I would come up with slightly different values. It would be nice to have an objective way to measure whose line is closer to the data points, mine or my friends, or mine from today versus mine from tomorrow. So one way to measure that is to say how far is each data point from what the trend line predicts. So I've got another column here called residual. That's the name for how far the y value is from what the trend line predicts. So if my true y value is 50 and my trend line value is 54, we usually do actual minus predicted. So 50 minus 54 is -4. So that residual is -4. This residual is positive 19.6. This residual is -8, and this residual is positive 14. And to get the trend line close to the points, I think we'd say we want the residuals to be small, right? So I could adjust these until I got residuals that I thought were small or something. But again, that's 4 values, and I'd have to trade off. Do I make this one small, maybe at the expense of that one? I'd like to have one number that summarizes all together how small are these residuals. So here's how I'm computing the residuals: actual y value minus the trend line value, the predicted value. So we could add up the residuals, but then sometimes the positives cancel the negatives, and we'll talk about that in just a sec. But it turns out that mathematically, usually the best thing to do is to square each residual, so you get all positive numbers and the negatives, there aren't negatives to cancel the positives. Square them and then either add them up or take the average. So here I'm taking the average, the mean of the squared residuals. So MSE stands for mean squared error here. MSE is a really common term in stats and machine learning and engineering. So the mean of these squared residuals is 172. Let's plot the residuals. Let's see, we can click that. So here, remember this residual, when I had this residual is -4, and here the black dot is -4, or it's 4 below the axis. This residual here was 19.6 and it was positive, so this black dot is 19.6 above y equals 0. And so these are the residuals shown as distances from 0 rather than as distances from the trend line. So we want to talk about the mean, kind of the mean of that group, but it's better to square each one so they all become positive, and the large ones get really large, and then take the mean of them. Now, would you say that these residuals kind of on average are 167? Think about that. Well, notice none of them are bigger than 50 or even 25, so it's kind of weird to say that the mean is 167 when none of them are that big. That's because the units here, I'm taking the mean of squared stuff. If this axis was in dollars, for example, then these residuals are in dollars, but the residual squared are in square dollars, which doesn't even make sense. So to put the units back into ordinary things we can understand, we often take the square root of the MSE. So we go from square dollars back to plain dollars. So we call that RMSE, root mean squared error. And would you say that 12.9 is kind of the average of these values? I mean, the largest one is almost 20, but then one's like -4. So hopefully you can think of that as kind of roughly the average of these in a squaring, summing, and then a squaring, meaning, and square rooting kind of way. We can talk about the mean residual, but it's really interesting. Here I've got Desmos computing the best possible m and b values, and the way Desmos defines best possible, just like the way Excel usually defines best possible for trendline, is the m and b that minimize the sum of the squared residuals or the mean of the squared residuals. So notice just by I got this line and I got 167.88 or 12.95 there. But I can go tell it to use the b that it found was the best and the slope that it found was the best. And now this is no longer 160 something, it's 120 something. And this is no longer 12 something, it's 11 something. So that's the best possible setting of m and b to get that trend line as close as possible to the data, to get the mean squared error or the root mean squared error as small as possible. And what happened to the mean residual when I did that? It's basically 0, right? This is just round off error, 10 to the minus 15th. So it is true that the mean residual ends up being 0, but you wouldn't say, well, then my mean prediction error is 0, because I'm not predicting everything precisely with 0 error. You could, instead of squaring, you could take the absolute value of the residuals, and that's called the mean absolute deviation. And that's not a bad idea. But there's good calculus reasons why we want to square instead of take the absolute value. One of them is squaring gives us parabolas, and parabolas have nice smooth bottoms to them, so a nice smooth optimum instead of an absolute value which has a sharp point. So it's easier to do calculus on things where the derivative is defined everywhere. If you want to get really fancy, fourth year statistics students see something called the Gauss-Markov Theorem that says squaring is better than taking the absolute value in many common cases. Okay, so the big picture here, if you have a set of values and you want to kind of summarize them, but you don't want to just take the mean because that might end up being 0 or the positives might cancel the negatives, a good thing to do is often to take the root mean squared error. It's very much related to standard deviation. If you've had a stats class, mean squared error is related to variance, which is in squared units. Root mean squared error is basically the same idea as standard deviation, and so that's a good link between the topics.